Hello everyone, so this is Rahul here, and today we'll continue our TCS NQT series. This is going to be our day two session where we're going to solve next five problems in our sheet. So let's start solving it. So the first problem here, what we're going to solve is convert a decimal number to an hexadecimal number. Problem looks like a very simple problem, but the concept which is being involved over there is not a very big concept, but a very fascinating concept, I should say. But because when I start solving this problem, it looks very simple, but if I get much deeper into it, trying to understand what type of conversions has been happen, it's going to be very interesting, right? So let's see what they have given. So given an integer num, return a string representing its hexadecimal representation. For a negative integers, two's complement method is used. I want you to get to know about this two's complement method. Why? Because we are gonna use this method also for your negative numbers. All the letters in the answer string should be lowercase characters, and there should not be any leading zeros in the answer except for the zero itself. Note, you're not allowed to use any built-in library method to directly solve this problem. Okay, so you're not supposed to use any built-in library method. You're supposed to use the method which is being conventionally used to solve this problem, like converting a decimal number to an hexadecimal number. Let's see some example. So when we give the number 26, it gives us the answers 1a, and as I say, as they have given, it all should be all in the lowercase letters. And it's minus 1, it provides us consecutive letters of f totally there are 7 to 8 think. So 1 2 3 4 5 6 7 8. Okay, 8 f's. Okay, right. So get to know about this question. So I'm very fascinated to give you the answer. Why? Because let's see the whole view. Okay, so what is the catch about this question is, so if I give you a what may I say, the decimal number, if the number is going to be 10, it's going to provide me the equivalent hexadecimal number. Am I right? Yes. So it's going to provide me the equivalent hexadecimal number. Let's give you the catch. So how we are going to solve this? So you guys know about it. To convert a decimal number to an hexadecimal number, you're supposed to divide the decimal number continuously by 16. Take the reminders in the upward direction. You guys know about it. Am I right? So I'm not going to give you the much. So let's give you an instance. Let's take the same example like called as 26. Okay, let's take the same example called as 26. So what I'm going to do is something bad. I'm going to divide 26 by 16. So if I divide 26 by 16, 16 one times is going to be 16, where I'm gonna give you a reminder as what can I say? I'm gonna give the reminder as 10. Am I right? I'm gonna give the reminder as 10. So 16 one times is 16. So reminder is 10, and remaining things I can't able to divide. So if I'm gonna take the reminder, take these things from the from the downward direction. So the equivalent number for 26, the base 16 is going to be 1, and 10 to the base 10. So and you guys know those things in terms of hexadecimal number. Sorry, I'm sorry guys, I'm sorry for that. Okay, so this is all about base 10, and this is all about base 16. Okay, and you guys already know about that. So when the digit crosses more than 9, that means 10, 11, 12, 13, 14, and 15, we are supposed to use the equivalent characters. Okay, what are those characters? Let's see. For 10, it is going to be a, 11B, 12C, 13D, 14E, 15 is F. So now the equivalent is going to be 1 8 to the 16. So actually we are supposed to reverse it, which is what can I say, 1 8 to the 16. Actually we are not sorry, I'm sorry guys. So it's going to be 1a. Am I right? So clear? So this is how the part is going to be. So for a positive number, since 26 is going to be a positive integer, it's going to be very simple. For a negative integer, let's call minus 5. How we are going to find the equivalent hexadecimal number? Okay, since minus 5 is a negative number, we are supposed to find the equivalent hexadecimal number for this element minus 5. How we are going to do it? So they've given us a hint in such a way that we are supposed to use a two's complement method to solve the negative numbers question. So how we're going to use it? So it's very simple, guys, but the thing is it's very fascinating too. Okay, let's see these things. Okay, first of all, let's convert this -5 to an equivalent positive decimal number. Okay, positive decimal number. How we're going to do is it's very simple. Let's find, first of all, to convert this -5 to an equivalent positive number, we are going to use the 2's complement method. So what is this 2's complement method? First, let's find what is the binary equivalent of the integer plus 5. So when we take the 8421 series, we are going to get 0 1 sorry 421. So 1, it's 1 0 1. So when we take the 8421 series, it's gonna be 4 2 and 1. So at 4 and 1 we are supposed to have the ones. Okay, now this is gonna be my the binary equivalent of plus 5. Let's take the ones complement. So the ones complement is gonna be 0 1 0. Why? Because I'm gonna totally invert all the bits. Now let's find the twos complement. So let's find the twos complement. I'm gonna add 1 to the digit, and I'm gonna find these things. So 0 double 1. So what is this equivalent? So 8421, I'm gonna have 3 as my equivalent. So for -5, I'm gonna have plus 3 as my decimal equivalent. Okay, so let's get back to this. When we started with -5, we represented -5 in terms of a positive 5, which is in terms of 101, and nothing but a 3 digit binary digit, 3 digit binary number. Its equivalent number is plus 3 to the base 10. We are gonna supposed to find another found that -5 equivalence positive decimal number is plus 3, and its equivalent binary number is 0 double 1. Let's find the number of integers present in between -5 and plus 3, right? So that's going to be our major cost. Let's find those things. So here it is -5, -4, -3, -2, -1, 0, 1, 2, and 3. Let's start. So 1, 2, 3, 4, 5, 6, 7, and 8. So there are totally in between, that means excluding -5 and including plus 3, from -5 I can able to reach the positive digit called as plus 3, the equivalent positive digit called plus 3 at eighth number. So it's very fascinating in such a way that we have taken 3 digit number as a binary equivalent, and we also taken the 3 digit binary equivalent. If I put 2 to the power 3 plus num what we have, that means plus 5 plus -5 what we have, then I can get the equivalent positive number. Am I right or wrong? Am I right or wrong? So it's almost curious about it. So let me give you another example. Let me give you another example. Let me take this time 16 as my answer. Like let's take -16 as my number. Let's take my num is equal to -16. I'm supposed to convert it to an equivalent positive, what can I say, positive decimal number. Let's find. So what is plus 16? What is plus 16? So we have 8 4 2 1, 8 plus 4 12, 12 plus 2 14, and so plus 16 goes behind the range, right? So let's take another number. Why? Because I'm not going to waste time much. I'm going to give you a hunt over here. Okay, let's take 10. Let's take -10. Okay, so what's plus 10 is all about? So 8 4 2 1. So I'm gonna have 1010 as my equivalent number. Now let's find the ones complement. So the ones complement is 0 1 0 1. And what's gonna be my twos complement? Twos complement is going to be 0 1 0 1 added with 1. So 1 1 0 carry over 1, and 1 I'm gonna have it over here, 0 1 0 double 1 0. So for -10, the equivalent binary number is gonna be 8421, that is plus 6. Okay, so might get into the clear view that let's find the number of digits between -10, which is 1010, to plus 6, the equivalent decimal number of minus 10, which is 0,110. So minus 10, minus 9, minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, and 6. Let's count the number of digits present in between. When the plus 6 is going to be reached, so I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16th. So at 16th digit, I'm going to reach my positive equivalent of the negative number. So it's very curious that minus 10 has been represented as 4 digits binary number. So when I take 2 power 4 plus num, I'm gonna get the positive equivalent of the negative number. Clear? Clear up to this? So this is all about matters, and this is all about matters, where I'm gonna take the power of 2. Usually we are supposed to work on these numbers, okay? Since we are working with some what can I say, convenience for some programming languages, we are going to take an efficient one, which is called as 64-bit as our answer, right? So 64-bit, I'm going to do is nothing but I'm going to work with the 64-bit. I'm going to work with the 64-bit. So what I'm going to precisely say that if my num is less than 0, then I'm going to make sure that my num is equal to 2 power 64 plus num. Okay. So what I'm going to do is something, but instead of finding the math dot power of 2 power 64, which takes me a lot time to consume, what I'm going to do is something, but I'm going to make sure to find one left shift 32 bits, which is equivalent to 2 power 64. Okay, which is equivalent to 2 power 64. Yeah, let's write the code for this. Yeah, let's write the code. So let's start writing the code. So first of all, as I said, for hexadecimal numbers, we are supposed to have the what can I say, the characters. As I said in the beginning, we are supposed to have these characters, so that once these characters are matched, we are supposed to write those things as a number. Okay, let's start writing the code. I'm going to write the pseudocode, and while we are executing it, we'll write the code in Python. Okay, let's start taking this. I'm going to take A is equal to 10, B is equal to 11, C is equal to 12, D is equal to 13, E is equal to 14, and F is equal to 15. I'm going to take it inside a data structure, a dictionary. Let's consider this. If my num is equal to 0, or num is equal to 0, or you can able to, so if there is things, I'm going to return the same num as my answer. And if my num, I'm going to return the num as my answer. And if my num is less than 0, what I'm going to do, I'm going to change the num into an equivalent positive number by making 2 power 62, which is 1 less than 32, plus num. So once we have done these things, so once we have done, what I'm going to do is I'm going to follow my same pattern over here, where I'm going to work on the digits. So while num is greater than 0, I'm going to find the digit. I'm gonna find the remainder when I divide by 16, and if the digit is present inside the dictionary what I have done, then I'm supposed to append. I'm gonna have the answer string. I'm gonna append it to it. Else I'll append directly the digit. And finally, while I'm returning it, I'm supposed to, what can I say, reverse the string, and I have to return the answer. Clear, guys? Clear about the first problem, converting a decimal number to an hexadecimal number. Okay, let's solve this problem. So this is what I have done. So I've started with cares of 10, 11, 12, 13, 14, and 15, which I have mapped to an associated characters. If num is equal to 0, then I'm going to return 0. And if num is less than 0, as I said, I'm going to make sure to add with the number with the 2 power 64 value, 2 power 64 value is equivalent to 1. When I'm left shifting the 1 to 32 bits, and I'm going to get the same answer. And final answer, the same thing what I done. If it is present inside the cares, I'm going to make sure to give the cares. If not so, then I'm going to do it, and finally I'm going to reverse the answer. That's fine. Let's give the same example what we have discussed so far. So we have 1A and FFFS as the answer. Let's solve this through the lead code through thing too. So let's submit it. Yes, so we have got the answer. Let's submit it. Yes. So yeah, so we have got this thing, and this runs with a beautiful time complexity where the number of digits has been considered. The only one thing you are supposed to note down here is nothing but your negative digits. If it is going to be a negative number, how we are supposed to convert that into an equivalent positive number with the help of this concept. Clear? Clear about the first problem of day 2? Okay, now let's solve the second problem, which is called as valid perfect square. Okay, we're gonna solve this. This is also a lead code problem, a valid perfect square. It's very simple problem, guys. Okay, so it's very simple problem. Okay, so given a positive integer num, return true if the num is a perfect square of perfect square or false otherwise. We can able to say a number is a perfect square if 64 is a perfect square. Yes, why? Because it is being it's we can able to say the square of a number, the square root of a number is 8. It's going to be an and whole integer. A perfect square is an integer that is the square of an integer. In other words, it is a product of some integer with itself. Yes, it's 8 times of 8 is equal to 64. And it has been advised that you must not use any built-in library functions such as sqrt. So it's very simple, guys, but I'm gonna what can I say? Ask you to solve this with a better time complexity where I'm gonna reduce all those things. Okay. Okay, let's start digging these things. So to find the number which is a perfect square, let me give you an instance. So if I want to solve to find whether 64 is a perfect square or not, I don't want to run my loop to entire 64 numbers, right? I can able to run my loop where like the half to the 64. That is what can I say? If I want to run my loop to 32, it's enough for me. And some of the series has been explained in such a way that you don't want to run the loop up to the 32. You can run the loop up to the square root of 64. But it is advised that I'm not supposed to use any method over there. I'm trying to run it with the half of the number. It's very simple. I'm supposed to find a number. If the number is divisible, if the number multiplied with itself to find as the number. So here I can able to give you an hint in such a way that we are supposed to find number. That is, I'm gonna search a number within the series from 1 till 32. That is 64. That is 64. That is 64 divided by 2. So I'm gonna search a number. What kind of algorithm I can come to? I can come to my mind in such a way that what can I say? Which will be less time complexity. Yes, that's gonna be the binary search. So I can also solve this problem with other constraints, but I'm trying to use binary search. Why? Because they can able to what can I say? Find the perfect number with the perfect time complexity. So you guys know about how binary search will work, and I'm not gonna give you much overview about how binary search is gonna work. Let's get back to the solution directly for the binary search. Okay, this is all about the valid perfect square. So if you guys know about that, what can I say? What can I say? The binary search is gonna work by by finding the mid value, and based on the mid value, we are gonna supposed to run those things. So if num is equal to 0 or num is equal to 1, I'm gonna return false. Why? Because we're gonna able to find those things. And I made it first is equal to 0 and last is equal to num divided by 2. As I said, I'm gonna run my loop until my num divided by 2, the half of the number, and I'm gonna find the mid value. And if mid times mid is equal to num, then I'm going to return true. If mid times mid is less than num, that is, if my multiplied number of both mid and mid is less than the value what I'm supposed to get, then the thing is, let's give you an instance over here. Let me draw and explain for you. One second. So if my mid times mid, so if my mid times mid is less than the num, that is, let me write a number line for you for this number line. Here it is num. Okay, here it is the if the mid times mid, the multiplied value of mid times mid is less than num. That means it is being present before the num. Here somewhat first and last is there. Then what I'm supposed to do is nothing but I'm supposed to increment why, because num is somewhere in between these things. Okay, I want to say that why, because mid times what I'm going to do, number somewhere in between these the what can I say, between these things. So if it is less than num, it is going to be a match in such a way that the number what we have multiplied is lesser. So what I'm going to do, I'm going to increment my first to mid plus 1, and it's going to be the other case. If mid times mid is greater than num, then it's very simple that we are supposed to decrement our number. What I'm going to do, I'm going to, what can I say, remove, I'm going to what can I say, decrement my last to mid minus 1. Yeah, so this is what the approach I have followed. So here the same approach I have followed. So like if mid times mid is less than num, we are supposed to increment our first, else I'm going to decrement my last. And if it is true, it is going to return true. If it is not going to available, then it is going to return false. Let's check for this. So we have valid square for 64, which is 8 times 10. I got true as my answer. And valid square of 12, there is no perfect square for the value 12. So it returns false as an answer. Let's see what is being given in lead code. So the same thing I have typed. Let's see this. Let's submit it. Okay. So we have got the answer. So got with the second problem, which is the perfect square, the valid perfect square. Okay, now let's get back to the problem number 3 to add two fractions. What can I say? This problem is not available in lead code, but you can able to know how to solve this problem. It's very simple. Why? Because I've gone through this thing with the help of examples. When I'm trying to learn these things, I'll give you with the same examples, and we'll try to solve the problem in the same way. Okay, let me delete these things so get to know about. I'll then draw you one more time to explain you this problem. It's very simple, guys. You are supposed to know the steps. Then before, after knowing the steps, it's very simple. Okay, so yeah, so this thing is, when I add, I'm going to take the example number 3 directly. Why? Because it might help us a lot. So 1 by 5 plus 3 by 5, this is going to be the example. So 1 by 5 plus 3 divided by 15. So how we will add these two fractions? First of all, we'll take the LCM of these two numbers, where the LCM is gonna be the highest number, the least number, which is multiple of both the number, which is gonna be 15. So 15. So what happens? What times will give you 15, which is 3. So we are supposed to multiply with this thing, and 15 times 1 is gonna be 15. I'm gonna have, so which is 3. So 3 plus 3 is 6 divided by 15, and it can be cancelled. It is divisible by what can I say, I can divisible by 3. So 2 times and 5 times, which is going to provide us an answer called as 2 by 5. The approach what we have done so far, like what we have did so far, like taking the LCM, multiplying with the numerator, and finding the value, and finally simplifying it. This is what we are also going to use in the same programmatically. So what I'm going to do something where you can, the first step here, what I've done here is to find the GCD of both the denominators. Okay, both denominator number 1 and denominator number 2. Why I've done so far this thing, why I've done these things is nothing but to give us a little more overview about the combination between the LCM and GCD. If you were aware about that. So what is the combination between LCM and GCD is that, let's find what is the combination of LCM and GCD. LCM and GCD is gonna be, when I multiply both LCM and GCD, then I'm gonna get the multiplication of two numbers. So now we have denominator 1 and denominator 2 and GCD, we can able to find LCM easily. But this is gonna be your case. You can also, find LCM directly by using your own method. But what I did is nothing but finding the GCD of both denominator 1 and denominator 2, and I combined both LCM and GCD to find the value of LCM. Then, so after finding the LCM, what I'm supposed to do after finding the LCM, I'm supposed to, yes. So this is what the LCM is. What I've done, I've divided. Yes, why? Because I have found the what can I say, quotient when I'm dividing with the number denominator one, right? So this is gonna be my quotient. So I'm supposed to find the quotient, right? So this is what I have done. I have found both the quotient and I multiplied. So when I divided by den 3 by den 1, I got the quotient and multiplied with den 1 and plus den 3 by den 2 divided by num 2, right? So this is what we have done, and we also added. So finally I got 6 divided by 15 after this step. So after step number 3, I've got the answer as 6 divided by 15. Now what I'm supposed to do, I'm supposed to, what may I say, I'm supposed to simplify this. So how I'm going to simplify this? The major important thing is a number can be divisible by both those things, am I right? So first thing, what I'm going to do is nothing but I'm going to simplify these things to a lowest term, right? Simplify these things to the lowest term. How am I going to do? So I'm going to supposed to find a number which divides both 6 as well as 15 in such a way that I'm going to give you an announcement. I'm going to give you the definition called as GCD. So after finding these two numbers, I'm going to find the GCD of both the numbers, and I'm going to divide the GCD, divide the numbers with the GCD. And finally, I get the answer. Yes. Clear? So what are the steps I'm gonna supposed to follow? I'm gonna find the GCD of den 1 and den 2, that both the denominators, and I'm gonna find the LCM directly with the help of GCD. And if you were aware, you can also use your own method to find the LCM directly. After finding the LCM, I'm gonna divide it with the values of denominator 1 and denominator 2 to find the value to be, which is to be multiplied with both the numerators, and I'm supposed to add these things to get these numbers. After finding these two numbers, I'm supposed to find the GCD of both the numbers in such a way that which can divide both the numerator as well as the denominator. Clear? Okay, let's find how I'm gonna supposed to find the value. Okay, so I've written a function called as GCD to find both the GCD's value. You can also use any one of your method. I've used the Euclidean GCD finding method, and lowest common factor, which is the thing, but to find the to find the values, the same thing what I've done. So let's find. So I've given you the same example. This is numerator 1, numerator 2, denominator 1, denominator 2. So let's give you an answer. It's 2 divided by 5 as my answer. Clear? Clear about problem number 3? So 2 divided by 5 as an answer. 2 divided by 5 as an answer. Okay, let's get back to the next problem, which is add the digits. So this is very simple problem, guys. Okay, but the concept what I'm gonna what can I say explain you over here is it's gonna be very fascinating one. So I'm gonna have a number called as 343. If I add this number, I'm gonna get 3 plus 4 plus 3, which is 10. And if I add the number one more time, 1 plus 0 is equal to 1. My return is going to be 1. So I'm supposed to add the digits recurrently in such a way that I'm gonna provide you I'm gonna provide you a one single digit as an answer. So you can solve this using a loop and you can able to find, but I'm gonna give you another overview which is called as digital roots. Okay, so what are these things? So this is this problem which has been available in lead code. So I'm gonna use an approach called as digital roots. What is digital roots? Let's take any number. Okay, let me take a number called as 459. So if I add these two numbers, what is gonna happen? 45. So 45, 4 plus 5 is equal to 9. 9 is gonna be my answer. So it seems that digital root depends upon the value called as 9. So what I'm gonna do is something where if the num is, so if this number is divisible by 9, am I right or wrong? Yes, it is. If the number is divisible by 9, then I'm gonna return by 9. Am I right or wrong? what can I say, if I return the reminder of when the number has been given to us, then it's going to give us the 9 as an answer. Let's take another number. Okay, I'm gonna take another number if it is, which is not divisible by 9. Let me take 4 8. So it was a 32, which is gonna give me as an answer as 5. So 3 plus 2, 5. Let's take another series. So now the number is not divisible by 9. But if the number, when I divide the number by 9, I get 5 as a reminder. I get 5 as a reminder. So I can also return num percentage 9 as an answer. Am I right or wrong? I can return num percentage 9 as an answer. In another case, if the num is equal to 0, then I can return num as the same, num as an exact directly, right? So this concept is called as digital roots, where I'm gonna play only with the number 9 to find the answer. Okay, so this is what the steps we're gonna follow. If num percentage 9 is equal to 0, then what I'm gonna do, I'm gonna return the what can I say, num percentage 9. Num is equal to 0, I'm gonna return num divided by 9. So let's go directly for our add digits problem. So as I said, return 9. Why? Because at each and every terms is going to be the same, and let me submit it. Yes. So I'm not used any of the loops over here, and I'm not used any of the constraints like it should be like this or it should be like that, kind of constraints. Just using an if condition, three if condition, two if conditions with one return value, three return values. I've done the thing. Yeah. Okay. Let's come back to the last problem of this TCS NQT day two, which is nothing but the Fibonacci number. So you guys all know about Fibonacci number. I'm not gonna explain you much, but what are the varieties can be asked in terms of Fibonacci number? So variety number one is going to be find the nth Fibonacci number when I give the number as input, and also it will also ask us to print the Fibonacci series up to. So you can solve the problem which is base two. That means these are the base two approaches. There are a lot of approaches, but I'm going to use only these two approaches using recursion without using recursion. Okay, and you guys know about how you guys know about how the Fibonacci series will work. Okay, you guys know how the Fibonacci series will work. Okay, so the Fibonacci series starts with the element 0 1, and adding these two things will give the next element, and adding these two things will give me the next element, adding these two things, adding these, and this goes on. So I can able to say f of n is equal to f of n minus 1 plus f of n minus 2, and f of 0 is going to be equal to 0, f of 1 is going to be equal to 1. So this is the concept behind the Fibonacci series. Okay, so what I can do, I can initialize a is equal to 0, b is equal to 0, c is equal to 1. Okay, and I can start adding these. I can start adding c is equal to a plus b, and c is equal to a. Yeah, sorry. What can I say? C is equal to a plus b. A is equal to b, and b is equal to c. Like this swapping is also possible without using any recursion. And you can also solve this using this expression, where I can able to write the recursion series of f of n minus 1 plus recursion series of f of n minus 2. You can use this thing to solve find the nth Fibonacci number, or you can also use to find the you can also use to print the series of Fibonacci number. Okay, so this is the concept behind, and I've used both the approaches here. So to find the nth Fibonacci number with the help of recursion, where I call the recursion with the help of number 9. Okay, the first thing is 34. Yes, the ninth number is 34. And the same using the without using recursion, I've swapped the numbers by adding consecutively from 2 to num plus 1. I got 9. And the same thing, Fibonacci series up to n, I've created a list called a series and appended the same thing. I've done the same concept over here. And 0, 1, 2, 3, 5, 8, 13, 21, and 34 is going to be our series. And here is also same thing. I've done the same thing, but here I've given you the series outside the function, which helps us a lot. Clear? Okay, so these are the 5 different problems which has been covered in TCS NQT Day 2. So the links of the problem are given in the description box, so you can use this, find the problem, and start solving by yourself. And try to come up with a better approach by using other concepts and give the problem with a better time complexity and space complexity, which will help you to solve the program. And we'll be continuing the series with TCS NQT day 3 and day 4. And thanks for listening.